Hello, and this video is going to be a few binomial examples just to get you comfortable in recognizing binomial random variables, and when you recognize them, being comfortable with answering every single type of problem that can be asked. Okay, so there's a communications monitoring company that has reported that 91% of all emails are spam. So suppose you're looking at 25 emails, okay? So X would be the number of emails that are spam out of the 25. Okay, so that's actually always asked in the question. So what's the probability that 18, at least 18? Okay, so what's the possible range of random variables? We don't necessarily have to set up the model. We can answer all these questions, but it's always a good idea to get to understand what's the possible range. If there's 25 emails, what could X possibly be? So as we know before, is the range of a binomial random variable will always go from 0 to however many trials you have. So we're looking at 25 messages. Okay, so we want to know what's the probability that there are at least 18 of them are spam. So I want to know from 18 up to 25. This is what you need to know. Okay, so this would look like this. This would be the probability that X is greater or equal than 18, which is equal to the probability that X equals 18 plus the probability that X is equal to 19 all the way to the probability that X equals 25. Okay, so how do we find this? Okay, with a calculator, can't find this to this. It can't find that. It won't go to the middle of a distribution. It won't go to the middle of a random variable and count to the end. But we do have a way. Of calculating a lot of these random variables without doing them individually by using the CDF function. Okay, so what's the complement of 18 to 25? Well, the complement from 18 to 25 is 0 to 17. So this is what we need to find. This is what we need to find right here. From 0 all the way to 17. And then we do 1 minus this. And that'll give us what we can't find on our calculator. So this is going to be 1 minus the probability that X is less than or equal to 17. Okay? So this is going to be 1 minus, and we want to do binom CDF. How many messages do we have? It's always N, P, X. This was on an earlier video. So we have 25 messages. What's the probability that any given one of them is spam? It's 0.91. And what's the highest random variable that I need to add to? I need to add from 1 to 17. 1 to 17. So the answer here, I pull in my calculator, will be 1 minus, we want to go to distribution, so it's second vars, scroll up to binomial CDF, because we want a lot of random variables here. Okay, and we want to say 25 comma 0.91 and 17. Okay, since I did 1 minus already, there's a pretty high chance. This is 0.999. So there's basically like a 99.9% chance that you have at least 18. Okay, that's what we just found. We found that. At least 18. Okay, what's the probability that there are 15 spam email messages? Okay, so this is an equal. This is not a greater than. It's just what's the probability that there are 15 in your box? What's the probability there's 15 in our box? So as per our formula, we have 25. This is a binomial formula. We have 25 emails. Okay, so 25 choose 15. And what's the probability that one is bad? That's 0.91. How many 0.91s would we have? Let me just write. This would mean that we had 15 spam and we had 10 that weren't spam. So I would have 15 spams, and the complement to this, okay, if this is 91%, then this is 9%, and I would have 10 of those. Okay. So then this comes out to be, I mean, we can't do this, but this right here would be binom. Now, since I'm only interested in one of them, this isn't exactly. Okay, so this would be a PDF. Not interested in a lot. Here I was interested in a lot of them. Okay, 18 and up. So this would be 25. The probability is 0.91. And we have I'm interested in 15 of them. Okay, so let's go second bars. Okay, binom PDF, because it's exactly. And we have 25 emails. There's a 91% chance that anyone is spam, and I want to know that I have 15 spams. Okay, so this is really small. So the chance that you're going to have this is okay. See, this is e to the negative 5, which means times 10 to the negative 5. So I'd go here and count over 5. So now if I start here, I need to count over, and this needs to be the fifth one. So 1, 2, 3, 4, 5. So that's right. So this would be a 0.00277% chance that there's exactly 15. Okay, so what are the mean and standard deviation? So before, we'd have to do 0, 1, all the way to 25. We had to find every probability, and then you'd have to do 0 times the first probability plus 2 times the second probability, all the way to 25 times the last probability. But luckily, since we recognize this is a binomial, we could just use the formula. So the formula is the expected X, which this is how many do we expect to have? How many spam emails should we expect? So the formula is n times p, which we've seen on the last video, and that is 25 times 0.91. This is how many we expect in the long run. 25 times or not even in the long run, even here. So we expect there to be 22.75 emails with spam. Okay, what's the standard deviation though? What's the standard deviation? Okay, so this is kind of like how much, if we looked at 25, how much can this go up or how much could this go down? So the formula for here is the square root of np 1 minus p. Okay, so that's the square root of 25 times 0.91 times 0.09. Square root of 25 times I'm sorry, not 25. See, this is NP right here. See, this is NP. So I have NP already. So I have the first two times together already, which is 22.75 times 0.09. Okay, so this comes out to be 1.431 emails. Okay, so the answer would be that and that. So we want to go up, say 1.5 and down 1.5 would be one standard deviation, but we have to kind of be careful because we're not sure if the distribution of all these x's are normal. Okay, so let's go to the next example. And here's the next example. It is known that 6% of people are universal donors. Suppose 20 donors come to a blood drive. What are the mean and standard deviation of the universal donors among them? Okay, so the mean is how many we expect. That's the expected number of donors. See, x is the number of donors. See, x is the number of, not the number of donors, number of universal donors out of 20 who show up. Okay. All right. So what is the mean? X is the number of universal donors. When I say E of X, that means how many expected universal donors should I expect out of 20, and that's n times p. So n times p would be 20 times 0.06, which comes out to be 1.2 donors. So basically we expect about 1, okay? 1.2 in the long run. So let's look at the standard deviation of x. Much variability is going on here. So this is going to be the square root of n times p times 1 minus p. So this equals to the square root. Now look, this is np. I have np already. So I see the np here. I could put this as 1.2 times 1 minus p. So if 6% is p, then 1 minus p would be 9.4. Okay, so it would be the standard deviation 1.2 times 0.94. Okay, which would be 1.06. So that's the mean, and that's the standard deviation. Okay, now what's the probability that they all will be universal donors? They all 20 of them will be universal donors. So this is a binomial, but you shouldn't need to use any of your binomial techniques that we're learning, because we know if they all are universal donors, that means all 20 would be universal. So we know that this would be 0.06 to the 20th, which is very, very, very unlikely. Okay, I won't even figure this out because it's going to be really, really small. Okay, what is the probability that there are at least 3 donors out of the 20 who show up? Okay, so at least 3, so I'll just write this. So probability of at least 3 is that. So this could, I'm looking for 3 all the way up to 20. Okay, so this is going to be 1 minus the probability that x is less than or equal to 2. Okay, this could also be written as the probability that x is less than 3. It could be written either way. These two things mean the same thing. These two things are the same. Okay, so hopefully you see why I picked 0 to 2, because that's the complement of 3 to 20. 0 to 2 is the complement from 3 to 20, and this is what I want. I want this. But the only way I could ever find it is if I did a PDF for 3, a PDF for 4, a PDF for 5, a PDF for all of them up to 20, and then add them all together. That's very difficult. But this is easy because you could do a CDF from 0 to 2 and then do 1 minus that. Okay, so this is going to be 1 minus a binom CDF. Okay, and that's going to be how many people came? I had 20 trials. The success of everybody was 0.06, and I want 2. Okay. is notation the other way would be 1 minus 20, choose 0. This would be 0.06 to the 0 times 0.94 to the 20. And I would take all this to 2. 20, choose 2. Because I need to add this from 0 to 2. And I'm just using the binomial formula right now. So if you guys are getting good at this, then you could see that this thing is the same thing as this thing. Okay, so let's go ahead and do this on our calculator. Let's move this in a little bit. This would be 1 minus second distribution. Let's go up to binomial. CDF, because I need 0 all the way up to 2. Okay, so I want 20, comma 0.06, comma 2. That's going to add 0, 1, and 2 all together. Find that, subtract it, so the answer will be 0.115. Okay. Okay, what's the probability there are 2 or 3 donors? 2 or 3. Okay, remember, or means add, because you can't have 2 or 3 at the same time. This means x equals 2 or x equals 3. The probability that those two random variables happens equals the probability that x equals 2 plus the probability that x equals 3. Okay, because you can't get 2 and 3 at the same time, so if it's an or, you could add them. Okay, so I'm going to do this in binomial formula notation, which would be I have 20, I want 2 successes. If I have 2 successes, that means I have 2.06s and I have 18 9/4s plus 3 successes out of 20, which means that I would have 3.06s and I would have 17 of these. Let's move this out of the way, which is equal to, now remember, to get this, it's a binom PDF, and that would be 20, okay, because I picked 20. My success for each donor is 0.06, and I want 2 of them, exactly, because it's a PDF. And I would add binom PDF. Here I have 20 again. The probability is the same, but I want 3 this time. So to get this, we're going to I'm just going to do the same thing as this up here, which is stat, which is second bars, go up to PDF. You don't have to find these individually and then do them. You just do it all in one line. So it'd be 20, comma 0.06, comma 2. Close it. Add that with the next one, which is the same thing. Up to PDF. Okay, verify PDF. I have 20. It's basically the same thing, but I have 3 successes this time. That equals 0.311. So about a 31.1% chance, okay, of getting 2 or 3 donors, which makes sense because we expect how many? We expect 1.2, so the chances of getting 2 or 3 are probably pretty good. Okay, what's the probability that the first 3 donors are not universal donors? So the first 3 people, so this is the probability of the first one not being universal, so that's UC, and the second one not being a UC, and the third one not being a UC. I just wanted to put this in here to kind of give you an old problem, okay, an old problem to practice at. So this would mean that they're all not universal, so this would be 0.94 to the third. Okay, so those are some examples that you guys could play around with to get good at this. The next video should be about turning this discrete random variable into a continuous random variable and make it into one of our favorite distributions, which is a normal distribution, which will happen. Okay, when the trials and the successes reach a certain number, the distribution of the random variables turns into a normal shape. So thanks for watching.